There we go. Anyway, so each one of these rings has potential energy. Energy of position. If I fall out this first story window, I'll probably hurt myself a little bit. If I fall out of the second story window, will I hurt myself more or less? A lot more, okay? Because it's got a greater energy of position. It's higher off the ground. The equation for potential energy is mass times gravity times height, if you remember that, okay? So the higher up I go, the more energy I put into my position. Yes? So the higher or farther away we go from the nucleus, the more energy we get in our position. So the nucleus, and every time you go out, gets more and more and more energy. So what these electrons do when we heat them is this. For my, oh, here it is, right here, yay. Okay, so the electron will basically absorb energy, jump to a higher energy level, we call that an excited state, but it can't stay there. So when it falls back down to its ground state, it gives off a wavelength. Just like the Broglie said, you know, we all give off waves when we move, but I'm just too big. You don't see my waves because my wavelengths are so small. But an electron is so small that when it moves, it gives off wavelengths we can see as visible light. Okay? So this one jumps higher. Because it jumps higher and falls down from a greater potential energy, it has a different wavelength. Then obviously if it jumped even higher and fell down, it'd probably have like a violet, because that's a lot more energy. Yes? Okay. So let's see. So we're going to quickly watch this video. It's about Bohr. And let me pause this. And then we'll watch this. There we go. I knew.
Shoot an arrow at a wall of gelatin, and you would expect it to pass right on through. Imagine your shock, however, if the arrow suddenly flew back at you. Okay, then, new game. But that is exactly the kind of shock physicist Ernest Rutherford received when he tried to penetrate atoms with something even smaller, alpha particles. In 1897, J.J. Thomson had theorized that atoms were similar to positively charged gelatin, with negatively charged electrons sprinkled around like bits of fruit. According to that theory, Rutherford's alpha particles should have punched straight through that flimsy atomic gelatin. And most of the time they did. But to Rutherford's surprise, a small number of alpha particles were deflected right back in the direction they came from. Right, they must be hitting something a lot harder than gelatin. Rutherford realized the atom must be comprised mostly of empty space, with an incredibly dense, positively charged core or nucleus. Hey, there's a marble in this gelatin. His student, a Danish soccer jock by the name of Niels Bohr, carried the ball a bit further. He proposed that the atom looked like a miniature solar system, with a dense center around which the electrons orbited. Things got a bit sticky when I tried to explain why the orbiting strawberries, electrons, didn't lose energy and eventually collapse into the nucleus. That's what Newtonian physics would have predicted. But modern scientists like Max Planck had rewritten some rules, showing that things like energy and light are not continuous streams. No. Instead, they are made up of individual packets of energy, called quanta. He even came up with a way to describe the size of these quanta, a formula known as Planck's constant. Bohr's atomic model would need some new rules as well. Bohr put Planck's constant to work, poring over his calculations day and night, probably to the distress of his fiancée. Their wedding was just a few months off. Almost there.
Time to take out our china powder.
Almost done, but it is peach Danish. I postulated that as long as an electron remains in any of several stable orbits, it will not emit radiation, nor lose any of its energy. I do.
I do.
Eureka! Bohr had unlocked a critical mystery about the nature of matter itself. What gives elements like gold
And helium.
their unique properties. Bohr understood that an element's chemical properties were related to how nearly empty or full the outer orbit or shell was. Lithium, hydrogen, and sodium, for instance, all have one spare electron, which allows each of them to bond with chlorine, a fellow in dire need of a single electron to complete his outer orbit.
Here, take one of my electrons. I don't need it. Why, thank you.
When two or more atoms share electrons that complete their respective outer orbits, they form stable molecules. For his work boring deeper into the atom's mysteries than anyone before, Niels Bohr received the Nobel Prize for Physics in 1922.
Okay, Mr. Bohr. So Niels Bohr